We'll do it at the end of the lecture. Come to me at the end of the lecture. Okay, if you're leaving, leave now in peace and quietness, please. You have to go through Banker's algorithm. Come on, hurry up, guys. Thank you. You don't have to shake hands with everybody. Come on, Aisha. Are you staying or are you going? Oh, not Aisha, the next door. Banker's algorithm. So how does a bank work? That's what this computer scientist wanted to know and maybe apply it to the computers. So what he realized is that a bank might have, for example, 100 million euros or dollars or whatever it is. That's total available at the bank, total cash. And then it offers loans, it opens for loans. So people come in and let's say we have 3 or 4 people or 5 people. So person 1, person 2, person 3, and person 4, they come and say, can I have a loan of, say, 40 million? And we approved it. And maybe 60 million or 70 million, 75 million, and 15, and whatever it is, I don't know, that's too little. Let's give 40, another 30 million. So we approve those loans. Okay. Who is doing the talking out there? If you're saying, please stay quiet. I don't know, I'm not saying it's you, but whoever it is who is doing the talking. Right, so if you see the total loans approved, 40 and 30 is 70 and 145, 160 million. Total is more than the bank actually has, but they do that. But for one individual person cannot ask for more than what the bank has. But in total you can. They can have 100 people and they can ask for 900 million and the bank only has 100 million, that's okay. But not one individual say, can I have 110 million? That's not allowed. That's the maximum for one person. But if the total exceeds, that's okay. So this is what's the maximum approved. This is what the maximum loan required by each individual. And when a bank gives loans to individuals, they want to make sure the money is not lost. The individual doesn't take the money and disappear on them. So what they do, they say, okay, what are you going to do? What kind of project you want to do? They want to know. And they say, okay, we're going to buy land, I'm going to build a factory, I'm going to bring staff, train them, and then get raw material and start manufacturing bicycles or whatever, scooters, and start selling them. So they say, okay, how much do you need to buy the land first? Then they say, we can't give you all the money now, but anytime you want to do any of those steps, come to us. So it comes and say, can I have 20 million, I want to buy the land and buy the equipment at the same time. So they give them 20. So this is already allocated to the person. Remember, the person is approved for 40, they've given them already 20. How much is left? Then we call it remaining or needs. Remaining or needed still, we have not got it. So they ask for 40, we get already issue them 20. So they might, after they're building, this is for actually building the building and buying the equipment, and then the training, when the training comes in and the staff, they start paying their staff, and then they buy the raw material. so that's for another 20 million left later on. This guy here needs 75. Maybe we only gave them, I don't know, 15 at this stage, and they still need 60 to go, and so on. So this guy might have given already, we gave him 10 and still needs 5. This guy, we might have given them, I don't know, 20 and still needs 10 left. So as you can see, the total amount given out so far, you can figure out, and how much does the bank still have in it. So let's say the total given out to individuals, they gave them 20, 20, 40, 50, 65. So this is the total. Total allocated is 65, right? 20, 40, 50, 65. How much is remaining? Money remaining at the bank, you know, in the till? 35. So we still have 35. So let's say this is usually a state of the bank, and normally at this time you can get a question. Is the bank safe now, or it's not safe? Is the bank in a safe state? What do we mean by safe state? Safe state, remember, just one other thing to remind you. This guy who is borrowing 40 million, they'll never pay us back anything until they finish building the factory and buying the equipment and all the raw material and everything. So they have to get the 40 million first before they start production, and then they start paying back. So everybody has to get the full amount before they start giving us back all the money. And then it's just a matter of time before we get all the money. So this bank will be considered in a safe, yeah?
What does it say on top of need?
Pardon?
On top of need. What does it say there?
Remaining. That's remain to get. Like this guy needs 40, got 20, and the remaining money is 20. Well, we call it needs. They still need the rest of the money. Okay, so this bank is considered safe if it can accommodate all of the customers with whatever money it has. With whatever money it has, it is in a safe state. So that's what you need to know, what a safe state is. A safe state, all needs can be, all remaining needs can be accommodated, can be satisfied. All of them, with whatever we have left. So we have 35. Can we accommodate everybody? Not together. We look for the one that only has very little left, and let's go and accommodate them first, satisfy them first. So if we say, if this guy comes in first, this is how you do it. If you are asked, is this system in a safe state now? This is what you do. Right, now we have 35. Can we accommodate? We can accommodate most of them, actually. We should have increased the numbers, but okay. Always go for the one that needs less left. You say, right, this guy asked for 15 million. He's probably starting in a small shop or something, or a small workshop. He got 10 million, now still 5 million left. There could be thousands, so don't worry about the amount, but just, so this guy still only needs 5. We have 35. Let's give them, so this is, you say, if person number 3 comes in, the sequence is so important. If person number 3 comes in, so I'm going to write here what's remaining, what's the balance left at the bank, which is 35. So if we give, out of the 35, we take 5, then now at the bank we have 30 at the bank. But the process 3, now this guy here, we'll give the 5 to that. So this 5 is given to this guy. So now this turns into 15. And how much is left? 0. That means we're finished with this guy. He's got all the money it needs. But now we only have 30. Instead of 35, now we have 30 at the bank. But the moment you give everything to that person, that means he got all the equipment, built a house, or whatever, the shop or a cafe, he got all the coffee machines, trained his staff, finished, took all the money. He's starting to work tomorrow on production. They start producing money and they pay us back. It's like in our computer system, if a printer has everything it needs, it has the files and the printer, it will print it till finish. Let's jump into the future and we say this guy's finished. Finished and pay us back everything. So this guy is going to pay us back the 30, well, sorry, this instead of P3, it's the balance, sorry, the balance at the bank. The balance at the bank is going to be 30. So first we took out of the 35, we took 5. But now the guy's going to pay us back everything he owes. So 30 plus 15 equals 45. So now we have 45. Who else can we accommodate? Who's the next person we can accommodate? So we started with process 3. Who's next? We can accommodate this one and that one. Process 1 or process 4? Let's go for the one with less needs. Let's go for process 4. So if we give process 4 the 10 euro, how much will be balance left with us? So we have, right now we have 45. And we take 10 out of it, so we have 35. But, so we give it 10, instead of 10, there's nothing left, and this guy now has 30. That means it got everything it needs, it got all the 30. Of course, it has everything it needs, it's gonna finish. In a month or 2 or 3 months, it's gonna pay us back 30 million. So the balance will be 35 plus 30, and that's 65. That's process number 4. So we finished process 3, followed by process 4. Now we have 65 at the bank balance. Who can we finish? We can both of them. So we start with the one with the least, then we give this one out of the 65, we give it 20, then we are left with 45, but this one is paid, all of it instead of 20, now we paid it 40. Okay, do you understand? Can you follow this? And then when they finish, they give us back 45, so maybe I should have done it while as well. So each one of them needs 2 steps. You take the money from the balance was 65. The balance is 65 minus 20, we gave 20. So now we have 45. And then when this guy finishes, it'll give us back 40. So it takes what's remaining, but when it gives us back the full amount, so from 45, and we get 40, that's 85. And this is process number 1. And finally, we do 2 more steps with process number 2. So finally, process number 2. We have 85, the new balance is 85. If we take 60 out of the 85, we give it to this one, it will give us back 75. And we will have 100 million left as a balance. So the point is, we can satisfy each and every one of them, all of them, one at a time. So that's what you need to go through. If you cannot satisfy them, if you get to a point, sorry, we're out of balance, well, then in that case you say, no, the bank is not in a safe state, or the system is not in a safe state. So, but I'd like to finish this just to see. So I'm going to put process number 2 up here at the top, but should be really at the bottom. So it starts at 85 minus 60. So now our balance is going to be 25. And when they finish, it gives us back 75. So 25 plus 75 equals 100. And all of them are finished, and we're back to full money. So all of these will finish. So first we'll take this one, we give it 60, and so we've given it here 75, and it will return the 75 to us. Sometimes you cannot do that, and banks always make sure that they can do that. They look at all their customers and say, okay, if this comes tomorrow and say, can I have the rest of my money? This is the way they do, and only in this sequence, and this is the safe sequence. This is called safe sequence. Process 3 finishes in first, and then 4, and then 1 and 2. There could be more than one safe sequence. Okay, this is called avoiding a deadlock. Because we have another example. And these resources, money, but they can be printers, or they can be files, or they can be hard disks. They can be resources. So let's look at another system. Let's say, again, we have a number of processes. Process 1, process 2, process 3, process 4. 4 processes. Okay, I might have to change some of the numbers here. So process 1 needs maybe 3 printers. This one needs 1 printer. This one needs 2 printers. And this one needs, 4 printers in total. We only have 4 printers altogether. In our system, there could be 4 or 5, but now I'll say 4. So this is the actual maximum required or requested by any program. This is what's allocated to each program. Let's say this guy, we've allocated them nothing so far. This one, allocated them nothing. This guy, we gave them 1, and this guy, we gave them 2. How many printers do we have left? Yeah, our balance or free printers is 1. So in order to work out is this system in a safe state or not, you need to work out the remains or the needs, remaining needs. How do you calculate remaining needs? What do you need? Minus what you've been already what you already got. That's what's left. This guy needs 3, got nothing, so it still needs 3. This guy still needs 1. This guy needs 1, and this guy needs 2. How many do we have left? 1. Is this system in a safe state? It's the way to do it. Can we accommodate? This is the question. Can we satisfy everybody and finish them all with what we have? Maybe. The best way to do it, go look for the one that has the least amount of resource, these 2. Can we give this to one of them? Yeah, if we give this one to this, how many will we have left? So if process number 2 comes first, our balance now is 1. But if we give it to this one, that will be 1 minus 1. So we give this one a printer. So our balance is 0. But that printer, then that means this guy got a printer now and doesn't need anything else. It needs 0. When a process has everything it needs, it will finish. And when this guy finishes, it will give us all what it has. How many does it have? 1. It has 1 printer, it will release it. 1 plus 1. No, sorry, now we got a 0. We turned into a 0 when we gave them our printer. So 0 plus 1. So this one didn't change anything. We still have 1 printer. We gave it to a process and it finished. And we got the printer back. So now our balance changes to 1 again. Now, we have 1 printer. Can we satisfy anybody? We can satisfy this one. So we started with process 2. Now we can go to process 3. And we can give it the printer. So we give it the printer. That means we have no more printers left with us. So from 1 minus 1 equals 0. So we have a 0 balance. But this guy no longer needs anything. We've given it now 2. It already has 1. We've given it another 1. It needs no more printers. It has everything it needs. It will release those 2 printers. When it releases them, we have a 0 at the moment, plus 2 equals 2. So now we're going to have 2 printers, which we can use to accommodate this one, and this one will give us 4, and then we'll accommodate this one, and this one will give us 3. So, the same steps, and the system is safe. What if this system here needed 4 as well altogether? I'm going to repeat the same operation just to... Same example, we have 4 printers in total. And we have the same processes, process 1, 2, 3, and 4. This one needs 3. This one maximum requires 1, and this one requires 4, and this one requires 4. And we have 4 printers. And this one has got 0 already allocated. Maximum and remaining. So this one still needs 3, this one has got nothing, it needs 1, this one has got 1, it still needs 3, and this one got 0, it still needs 4. Or even 2, doesn't matter. 2, sorry, this one had 2 and 2. Sorry. All right. We have total of 4 printers. How many did we allocate? We allocated 3, total allocated. How many left remaining with us? 1. Can we satisfy anybody here? Yeah, we can satisfy process number 2. We give it the 1, so then our remaining is 0, and this one got a printer, doesn't need any more, and finish. And then when it's finished, you give us back 1. So we'll have 1. Right, but normally I need to write it twice here to calculate. Now, so process number 2 is gone. We have 1 printer. Can we accommodate anybody here? No, we cannot. So this system will not finish, will not be able to satisfy all the requirements of all the customers, and therefore it will not finish, and it's not safe. Not in a safe state. Whatever got it in safe state, maybe the last time this printer came up and said, can I have 1, or this one said, can I have 2, they gave it 2 wrong. They shouldn't have given it the 2. Should have told us to wait. So this is known as the banker's algorithm. I already have a video on your page, on your Moodle page, that gives an example of one with a deadlock and one without a deadlock. So if you are given a situation, a state of a bank, or a system with a number of resources, total amount of resources, sometimes you're given the total number, and sometimes it just tell you already the total allocated is 3 and there's only 1 remaining. Or they tell you what's the total and you have to work out what's the remaining number of resources. And you need one of these columns for each resource, for printers, for hard disks, for sometimes 3 or 4 resources. The table can have 3 resources for each instead of allocated. It's just 0, it could be allocated 1 to 1, 2, 3 or something like that. So 1 for each kind of resource available, and it can be calculated for if you can allocate all the resources or not. But every process must get everything it needs before it gives you back what it has. So in this particular example, there's a deadlock. So we're going to have a look at a couple of examples on the slides and see if you can figure out whether the system is in a safe state or not. So when do we call a system is in a safe state? Anybody knows what the answer? If you're asked, what does the term, the system is in a safe state? How do you explain that? What is a safe system, yeah?
Safe state is when all needs can be satisfied. All the current needs.
Yeah,
to
all the processes, all their needs, they can be satisfied and they'll terminate with whatever resources we have now. Okay, with whatever is remaining number of resources. So that means the system is in a safe state. Let's get back to the slides and we take it from there. This algorithm was actually brought or invented by somebody called Dijkstra. He's a computer scientist, but it's called the banker's algorithm. It's known as the banker's algorithm. So here's an example. There are a number of customers, and they ask for a number of loans. This is the maximum credit they asked for, 4,000, 5,000, 8,000. This guy already got 4, this guy already got 2,000. Is this system in a safe state or not? First, you need to work out the remaining needs. This guy asked for 4,000, we got nothing so far. I mean, still, you can come back tomorrow and say, can I have my 4,000, the remaining? This guy has asked for 5,000, already gave him 2,000, that means the remaining is 3. And this guy asked for 8,000, we already gave him 4, there's still 4. Is this system in a safe state? Well, it depends. How much do we have in the bank altogether? The total capital fund is 10,000. You need to know how much is left. How many did we allocate and how much is left? What's the total allocated? Total allocated is this one. We gave 0, 2004, that's 6,000 given out. That means we still have 4,000. Can we satisfy everybody with 4,000? This is the remaining. You look for the smallest, 3,000. Say, yeah, we can finish this guy. So out of the 4, we give 3. So we are left with 1 in the bank. But soon this guy will finish and give us back 5, then we're going to have 6 left. Okay? Now we have 6. We can accommodate anybody. We can give this guy 4 out of the 6. We'll have 2 left, but this guy will take the 4 and bring them back to us. So back to 6 again. We come down to this one. We give 4 out of the 6. We have 2. This guy will take 4, but give us back 8, and 2 is 10. So we're back as the full, and everybody can be satisfied. So the bank in this state is in a safe state. Okay, so, but of course, if you are asked in a test or an exam, it's in a safe state, but you need to go through this process, prove that it's in a safe state. You say, okay, we have 4,000. You need to find out what's the maximum given. We already given 6,000 total loan, but the bank altogether has 10, so the remaining in the bank is 4. We can accommodate, start with the smallest requirement. Right, so, and you need to find out the sequence of, who's going to finish first. And there could be more than one sequence. You don't have to start with the smallest, but that's probably the easiest, best way. But you can start, if you have 4,000, you can accommodate that or that or that. Either one of them, you can start with it. And here are the sequences maybe at the bottom. So let's go to the next one. The next one. Imagine this situation. There's another problem. This is a different problem. The bank has a total of 10,000 and has already agreed to give 4,000, 5,000, 8,000 to those, which is probably similar to the previous one, 4, 5, and 8. Exactly, it's the same. But this guy has already got 3,000. So that's probably one of the differences. This guy got 2,000, this got 4,000. The total we gave out is 9,000. We only have 1,000 left. Can we accommodate any of them? None of them. The system is not in a good state. Sometimes, because if this guy only got 2,000 out of the 3 and then, no. Okay. So anyway, this system is not in a safe state. Let's look at this one. Another problem. Imagine this is a computer system and we have a number of printers. We have a total of 10 printers and programs come in. This guy wants 4 printers or files or whatever the device is. This guy needs 4 devices, this is 5 and this is 8. We only have 10. Remember, no single user can ask for more than what we have to start with. So now, we've already given out 6 devices to those 2 and 4 out of 10, so we have 4 left. Is the system safe or not? Safe. We can accommodate this one. So if we give this one 3 out of the 4, so we have 1 left. But when we give it, it will give us back 5. So now we have 6. We can accommodate that one, nothing will change. Out of the 6, we give it 4, and then when it finishes, brings back the 4. We're still 6. We come down to this one only needs 4. So that's a safe. Okay, well that's probably an example of unsafe state. Now this is the idea of avoiding a deadlock. This is your system is reasonably safe. If you get into an unsafe state, you're very close to a deadlock. Avoid it. Don't put yourself in an unsafe state. Unsafe state, that means you're very close to a deadlock. So when somebody comes up with a request before you actually give them approve the request, see, is it going to turn you into an unsafe or not? Like, for example, you're in a bank and one of the customers can say, can I have 2,000? You say, hold on, wait. Let's go and simulate as if we've given them the 2,000 and change the tables and then see, is the system still going to be safe? If it's still going to be safe, we'll approve it. If the system, by giving those 2,000, turns into an unsafe, we'll refuse that request. So if somebody comes with a request, don't say, okay, there you are. You know, you've asked for 10, you already had 3, you're asking now for 4, we give them to you. No, before we give them, let's pretend we gave them and we see if our system is going to be in a safe state. Okay, so this is another example if you want to work it out. Usually you'd be given a table, something like this. There are 3 users or processes, A, B, and C. This one needs a maximum of 9, this is 4, this is 7 devices. But this has already got 3, 2, and 2. Is this system safe? Well, how many systems do we have? It says this one we still have 3 left. So the total amount of system that we have, we've already allocated 3, and 4 is 7, and 3 is 10. So it's the total of 10 devices. We've already given 7 of them, we still have 3. So obviously with the 3, you cannot accommodate any of these guys. If you pick the smallest one, which is 4, you only have 3 left.
No, it's like you have to.
Oh, sorry. Thank you very much. Yeah, I was just testing you. Good. All right. So this guy only needs 2. That guy needs 2. That guy needs 3. We can accommodate them all. No. That's what they have. We need to create another column. That's the needs, the remaining. So this guy still needs 6. This one needs 2. This one needs 5. And so we're gonna go for the B, for B. Is this the same system? Yeah. So that one only needs 2. So if we take out of those 3, give it to this one here, you'll have the other 2, and then give us back, the 4. So we're gonna have 5 at the end of this. So if we take 2, we give them to B, that means we have the balance. We took 2 out of our 3, we have 1, but then when it finishes, it give us back the 4, so now we have 5. This guy needs 5, he still needs 5. 7 minus 2 still needs 5 out of the 7. We only got 2 so far. So we can give our 5 to C now. So now C will have 7. We will have nothing remaining, but this guy will finish and give us back the 7. Now we can look at the top one, it only needs 6. So we give it 6, we have 1 left, but then it gives us back the other, all the 9, and we get back. So yeah, the system is in safe state, and the safe sequence is B, C, and A. It's important to find out the safe sequence. So this is how Banker's algorithm works. And it works, you can avoid deadlock. Somebody say, can I have more? You say, hold on, we check, will that turn our system into an unsafe state? But what's wrong with Banker's algorithm? First, all the jobs need to tell us in advance what resources they need. Some jobs don't know what resources they need. Or to be on the safe side, they say, okay, they'll give you even more resources than they need. And the number of total resources for each class must remain constant. Like if we start working with 10 processes and we have number of resources, we cannot change while we're dealing with those processes and resources. If another process starts, we have to start calculation anew. So it's not really very flexible way of doing, calculations. And the number of jobs must remain fixed. If another job comes in, we'll have to recalculate. Overhead cost can be quite high, and also you're looking for the worst case scenario. Maybe a process takes 4 resources but doesn't always need them. And it takes them from the start when only needs them for a little short time at the end. So it's not an efficient way of solving the problem. Banker's algorithm is not an efficient way because it looks always at the worst case scenario. Yeah, a program sometimes works and maybe ask the user, what do you want to do? Sometimes say exit and finish. So even though it could have used 5 printers, or it could have used only 1 or nothing. But yeah, the maximum is 5. So you always have to take care of the worst case scenario even if you're not using it. And that's not an efficient way of running programs. Scheduling suffers as a result of poor utilization and jobs are kept waiting for resources. So it's like you book all the resources in advance even though you don't need them all the time. It's like you say to yourself, okay, just in case I need it, I'll get it just in case I need it. And okay, sometimes you need it, but most of the times you don't need it. So it's not really a great system. Okay, do you want to work out if this is a safe system or not? And if it is, what's the safe sequence? You really need to create, in an exam or test, create another column. We call it what's remaining, what's needs for each process. This one approved for 7, it's already got 2, you need the number 5 here, still needs 5. This one still needs 2, this one still needs 3, and this one still needs 7. 7, 2, 3, 5, 2, 3, 7. That's what the remaining. How much do we have? You need to find out. The total is 9, but the allocated is 2, 4, 6, 7. So we still have 2 in our hand. And I think we could accommodate this one, because that one still needs 2 only. We can give it the 2, and it will come back with 3. Now, this one still needs 3, we can accommodate it, and it will come back with 5. Now we have 5. This one needs 7 and that one needs 5, we give this one. So yeah, it looks like it's a safe, but you need to specify. So the sequence was process 2, process 3, process 1, process 4. So this is really what you should be doing. Create a remaining and available. So there it is. That one still needs 5, this one still needs 2, this one still needs 3, and this one still needs 7. Total allocated is 7 out of 9. We still have remaining 2. 2, we can go for this process. Give it 2, it will finish and come back with 3. So now we have 3. But now the system has a different shape. Where's the shape? Oh, that's a different example. Right, so with the 3 we can accommodate this one. We give 3, we come back with 5, and we have 5. That one, then we give that 5, they come back with 7. 7, we give this one 7, they come back, we'll have 9. Can you follow it? Can you fill the table? Here's an example that you should try. This system is safe. Assume, was it the last system? Yeah, it's the last system, 7359. Yeah, it's exactly the same system. So this system we've established it's safe. Now what happens here if this process number 3 comes and say, can I have one resource? This is exactly the same example. Same number of resources, same maximum allocated. But now process 3 says, I need one more resource. Should we give it or not?
No.
Why not? Let's try it. Let's give process number 3 one more resource. It asks for 5, we give it another resource, becomes 3. And remaining is 2, I think. But now how many are left with us? The allocated is 2, 1, this becomes 3, so 3 and 3 is 6, 8, we have 1 left. Is that safe or not?
I'll say.
And now this is the after if, like somebody says, process number 3 asks for one resource. Don't approve it yet, but let's imagine, let's go ahead and pretend we allocated it. So now process number 3 has 3 out of total 5. Let's create the remaining column.
It's unsafe.
So now that's the situation. This one needs 5, this one needs 2, this one needs 2, and this one needs 7. We've already allocated 2 and 3, and 3, 6, 8. Out of total of 9, that means we only have 1 left. Can we accommodate any of them? No, we cannot. That means we should not approve that request. So process number 3 comes and says, give me one device, because you've already asked for 5. Now I have 2, can you give me another one? I had 2, can you give me another one? And if we give it this way, we only have 1. We will not be able to accommodate any process. That means our system, if we approve this request, our system will go into unsafe state. We say, no, you wait. We don't give that resource. If another process asks for 1, maybe, yeah, we give it and then we are still safe. Imagine if process number 2 had asked for 1. That would be completely different. But this one, imagine process number 2 has asked for 1. This is exactly the same system. But process number 2, instead of 3, asked for 1 resource.
It's safe.
So if we give that resource,
Yes.
so now it has 2 resources. So we need to work out the remaining 5, 1, 3, 7. And how many is available in our store? Well, they allocated 2, 4, 6, 8, 1. Good. So with 1 here, can we accommodate any of those? Remember, this one still needs 5. This one needs 1. This one needs 3. This one needs 7. Yeah, we can accommodate this one. So if we give 1 to this one, it will bring us back 3. 3, we can accommodate this one because 5, maybe we should, I hope it shows the next, yeah. Yeah, this is the way it works. See, when we gave process 3 1, the system turned unsafe. But if we gave process 2 1, process 2 asked for 1. Imagine we pretend we gave it the 1. So now it has 2 and only remaining 1. And 1 is left in the system. We can accommodate that one. That will bring us back 3. The 3 can be used to accommodate this one. That will bring us back 5. The 5 can be used to accommodate that, and then bring us back 7, and the 7 accommodate this. So process number 2 asks for 1 resource, we will approve it because it does not turn our system in an unsafe. If process 3 has asked for 1 resource, we would refuse it because it would turn our system unsafe. If you understand this example, the last example, why one process asks for 1, we approve it, and another process can ask for 1, we do not approve it, because it turns our system unsafe. So that's a question that's sometimes asked. What if process number 1 asks for 2? Shall we give it to it or not? And you have to go through it, and if you can clear everyone, you say, yeah, it will not make our system unsafe. We can still finish everything. So this is called deadlock avoidance. You keep avoiding a deadlock. Every time a process requests something, you say, hold on, let me check the system. and pretend you gave it and calculate it. Is it going to turn us into unsafe? And if it is, well then say no. We cannot approve that request. Okay, detection, we've already worked out how to detect a deadlock. Imagine it's this system, we say one process number 3 can finish and release this resource. Now resource 3 can be given to process 2. See, pointing at number 2. Now process 2 has everything. It can finish, release the resources. Now resource number 1 is free. We can give it to process 1 and it finishes. And if we can finish everybody, all the links go, that means there is no deadlock. This system probably has a deadlock, so you need to go through those systems and find out whether they have deadlocks or not. We've been through those. Finally, recovery. 5 minutes left. If we already have a deadlock, see, we try to prevent it. If we can prevent it, we avoid it. If we can't avoid it, we get stuck in a deadlock. Deadlocked processes, they'll never come out of the deadlock. Because each and every one of them is asleep, waiting on another one who is asleep, waiting on another one in a cycle of sleeps, cycle of waiting and sleeps. So they're all asleep, they're all waiting on one another. So they'll never come out of a deadlock. It could have happened to you many times, and probably your laptop got stuck in a deadlock of some processes, and one of the solutions is switch it off, power down, reboot it. That's one solution. That's the worst solution. That means you're killing all the processes that are running and that are deadlocked. The ones that are deadlocked and the ones that are not deadlocked. So usually there's a better way. If we can identify which resources are deadlocked, as we did with those diagrams, if we know which processes, because remember, if you have 50 processes in a system that are running, only one of them is actually executing at a time. The rest of them are all waiting. They're either waiting on a CPU, or waiting on a printer, or waiting on something, and the printer is running and the hard disk is ticking. There's so much noise, so much activity, but only one of them is running. But all the others, the 49 that are waiting, which one of them are awaiting permanent wait? That means a deadlock. And which one of them are waiting and they're going to get their resource soon. So we've done the diagram that we used earlier on to show us the resource allocation diagram that shows you which ones are really deadlocked, if you can pinpoint them. Then you can come out and only terminate those deadlocked processes. So if you have 50 processes running, only 4 of them are deadlocked, go to those 4 and terminate them. Why terminate all 50 processes that are already running? Some processes can cause you a lot of problems if you terminate them and run them again. Like if you are deducting money off customers, and then halfway through you stop and then run it again. So some customers are being deducted twice. So it can cause you a lot of errors, a lot of mistakes. You won't see them. The computer won't stop and tell you there's an error, but your calculations will be done twice when they should have been done once. So terminating all the processes is not a good idea. Only find out which processes are deadlocked and terminate them. But also those that are deadlocked, there's a better way, only terminate one of them. If you terminate one of them, it will release the resources. Maybe that's it, that's the end of the deadlock. The others will start work and will finish. So this is a better way of getting out of a deadlock, is to first identify which jobs are deadlocked and then pick one of them only as the victim to be terminated. The one that will cost you less trouble, that will cause less cost, the one that has not, if for example, 2 processes, one has been using the CPU for 10 minutes, and that's a long time, and one has been using the CPU for half a second, which one would you terminate? Because remember, the one you terminate is going to start running again later, and it'll do all the work. So the one that's been running for 10 minutes, that's done a huge amount of work, it's better not to cancel it. Cancel the one that's done very little work. So you're not really losing much, all right? So you terminate the one that has not been running for much time, the least amount of time. Also, some processes, they might be running for a long time, but they do nothing. Maybe they just display nice pictures on the screen. They can display them again. But if a process is updating records on files, writing to files, do not terminate them. They are so dangerous to terminate. So, to recover, switch off the machine, terminate all processes, or only terminate the processes that are deadlocked, or even the one deadlocks, just pick one of them and terminate it. So this is the technique, you know, the best technique. Just pick one of the deadlocked. Which one of them? Sometimes, some jobs, they actually keep a record of what they are doing. For example, if you're downloading a video or a file, and you lose the internet, for example, and then you get the internet back. Sometimes you start downloading the video again. It could be 10 minutes, 15 minutes, start at the beginning. And sometimes some programmers are really good. When they're downloading, they keep track of how much they downloaded. If they lose the internet, they say, oh, we lost the internet at 70%. Exactly, they know how many bytes they read from that file and saved it. So if they start again, they already have a little log. How many did we save? So they start exactly at the point where they stopped and they finish. There are jobs that keep snapshots, or they keep a log of what the work they're doing. If, for example, you're updating maybe staff records, you're adding 10% to each staff. So every time you update a staff, you write here, I reached this staff number. So if they're to run again, they say, did we run earlier? Yeah. Which one have we reached? And they go to that one, they continue. So some programmers are really good. They keep a record of what they do. So if their program is interrupted and runs again, they know exactly where to continue from. But some don't. So if you know this job that you have already keeps a record and knows exactly where to stop, then it's okay to stop it. Because when it starts again, it's not going to run again the full blow thing. So select stop new jobs from coming into the system, but usually that doesn't do it. Usually you have to pick the job, one job, and terminate it. So which job would you terminate? Some people say, look at the priority. Priority 1, that's the highest priority, don't terminate it. Priority 9, which is the lowest priority, terminate that one. That's a good idea. Because priority 9 probably just runs and plays some pictures or some music, and then doesn't do any really work that's dangerous that can. Priority 1 is probably updating, it's really important. So that's one choice. High priority jobs, don't touch them. CPU time used, how much CPU time was used? CPU is like if a job has been running for 5 or 10 minutes, that's a huge amount of work that was done. And it's about to finish. Don't waste all that time. Leave it running, go for one that has just started. Look for the one just started and has less CPU time. The number of jobs that would be affected if the job were selected as a victim. Like one job is waiting and it's holding 5 resources. Another job is waiting, it's holding 2 resources. You better go for the one that has 5 resources. Because if you terminate it, all these resources are available, they have a better chance of releasing the deadlock. Finally, the jobs that are modifying data, don't touch them. This is, don't touch. If you know this job is updating files, rerunning it again can be a big problem. So these are kind of recommendations. If you are asked, which job would you recommend to release or to terminate in order to get out, to recover from a deadlock? So you pick the one, you give those recommendations. So terminate the low priority jobs, or terminate the jobs that do not update records, or terminate the jobs that has a lot of resources. So if you terminate it and release many resources, you have a better chance. Or the jobs that have done very little CPU time, the least amount of time. So these are some recommendations. That's it. That's something called starvation. Starvation is not getting a resource for a long time. It's like a deadlock. But a deadlock only happens between 2 or 3 or 4 processes. It never happens to a process on its own. Remember, a deadlock, at least 2 processes. One takes a resource and needs another one. The other one takes this resource and needs your resource. But starvation is if a process, one single process can be starved by itself. Like a low priority job. A job that needs the CPU, but we are running priority system. It's always at the back of the queue. Every time it gets close to be executed by the CPU, more processes of higher priority come in. It's pushed back in the queue. So it can be left in the system for a long time, for minutes or hours or even days sometimes, until the system, all the important jobs are done and no more important jobs, then it gets its chance. So that's called starvation, not getting a resource for a long, long time. And the difference between starvation and deadlock never happens to one process. Deadlock always involves at least 2, maybe 3, 4, 5 interlocked together. One is waiting on the next one. But starvation can happen to one of them. This is finally the example of, somebody came up with this idea, the dining philosopher's problem. So somebody came up with this idea. In China, in some parts of China, there are these monks who go on their own and meditate, think, and they have nothing else to do except thinking. But they also get hungry every now and again, so they have to eat to continue thinking. So, imagine, and in order to eat, they need those chopsticks. They need a pair. So, assume they are each on each seat, there are one on each side. So the monk here can pick the one on the right and the left and use them to get some of the rice and eat. This is just describing the problem. And there are, in this example, there are 5 of them. Sometimes they get into starvation mode, and sometimes they get into a deadlock mode. How do they get into starvation? First, these tools that they're using, they're shareable, but not shareable at the same time, which means they are dedicated. That means, in order to eat, each one of them needs those 2 chopsticks, the one on the left and on the right. So, for example, if A here, for example, on the left here, picks the 2 chopsticks to eat, and if this guy here on the right picks those 2 chopsticks to eat, this guy, if this guy gets hungry, while these 2 on either side are eating, this guy will not be able to eat. Look at it from another perspective. This guy is eating, the one on the left. That means the one on the right here, when it's right, cannot eat because the chopstick is missing. So he goes to grab it and it's already missing. So I say leaves it. Then he goes meditate or sleep for a few minutes or 10 minutes or half an hour and then comes back again. This guy is already finished, but the one on the right started eating. So took the chopstick from there. Of course, when they finish with the chopstick, they wipe it clean and disinfect it and put it back so it can be used by someone else. But this guy here, if this one is eating, that chopstick is gone. This one here cannot eat. Needs the 2 chopsticks. Goes to sleep for a little while, this guy finished, put the chopstick, but this guy wakes up, picks those 2 chopsticks. So this guy wakes up and finds the chopstick on the right is missing. Goes to sleep. And if these 2 guys keep eating alternatively, this guy will get not deadlocked, but will get starved. I mean, it keeps missing its turns. It might get its turn, but it keeps missing its turns. That's called starvation. That's an example of starvation. A deadlock example, imagine if all the monks were sitting around the table, at the same time, they're all thinking and contemplating, and then suddenly they all got the urge to eat. Imagine this. They all opened their eyes at the same time. They all extended their right arm, picked up the chopstick on the right. So this guy got that chopstick on the right. This one got this chopstick on the right. Each one of them got the chopstick on the right. And then they go to get the left. It's gone. So you say, okay, I'm holding this. I'll wait on the left. Each one of them has the right chopstick, and each one of them is waiting on the left hand. And they're not releasing it. There's no preemption. And they end up in a circular wait. And that's a deadlock. So that's an example of a deadlock. So can you think of any algorithm or a sequence or commands or rules you tell them that if they follow at the minimum cost, of course, don't tell me, okay, well, you can have a computer program to tell them which one to eat. But we want just that simple instructions. If they follow, they will not fall into a deadlock or starvation. Any suggestions? And remember the rules. Each one, in order to eat, they need both two chopsticks. And there's no knowing time when a person needs to eat or feels hungry. Hold and wait is a good example. You say, okay, if you take the chopstick on the right, and then you go for the one on the left, and it's not there, don't hold the one on the right, put it back. Maybe. But then, okay, that's fine. If this guy is eating, this guy now wants to eat, picks that one, it's not available, this one is missing. So he puts it back, and then I say go sleep for a little while. This one finishes, puts the chopstick, but then that one starts eating. Picks that one and then this one wakes up and that one is missing on the right. It might help solving the problem. Telling them you can't hold the chopstick waiting on another, release it. Okay, that will remove this deadlock. Any other suggestions? We don't want these guys to starve, and we don't want them to get deadlocked. Any ideas, guys? You can put an order on who can eat first, for example. You might, I don't know, if they have numbers, if you can say, okay, the odd numbers can start eating. For example, number 1, and then number 3 each, and then skip 1, 5, and then skip 1, maybe. That might solve the problem, but we don't always know what time this guy wants to feel. It might be their turn, but they're not hungry. So maybe we can skip it. We say, if they're not hungry, pass it on to someone else. That might solve. These are the kind of solutions we're looking for. Something that can solve the problem without much extra resources. Okay, they need to number each, we have to number them. But of course, someone else might say, okay, we have a supervisor standing up beside them. You can eat, but that's, extra cost, way too much. We kind of would like a solution, a self-given solution that if everybody follows, it will solve the problem. Okay, maybe I'll leave that for you to Google it and see if there are any solutions to, you have a solution? I see the hand is going up, go on. Okay.
So, we based on importance and priority. Like, who's hungry at the moment and who can do it.
So you can identify that probably answer yours. Go on. Priorities. We give them priorities, but they are equally, they have equal priorities. We give them numbers, 1, 2, 3, 4, 5. Yeah. The least hungry. Listen, we're here with me. So it might wake up one day and say, oh, I'm starving. I could eat okay. I don't know how to measure, well, you're making it really complicated by measuring how hungry this person is. But let's say we got, everybody says, give us a number, how much you're hungry from 1 to 10. And one says, I'm 7, and one 3. That means 3 is not very hungry. Yeah? So?
And we are able to gotta take the chopstick
To the one who is most hungry. Okay, okay, it's not bad, but it's kind of slightly over complex. But okay, if you can reach a function that can measure how hungry you are. Anybody else with any other solution?
If someone is their turn, their priority increases for the next turn.
Okay, so we give them priorities, and if they miss their turn, we
Yeah, if they're with their turn, their next turn, so they can get their chances.
okay, not bad. All right. And so we have a counter here in front of each one of them, and if they miss their turn, they increase the number by one or decrease it by one, depending. Increase the priority. Yeah.
Maybe we can add quantum.
If we can do it without extra functionalities and resources, or at least less resources, okay, priority number can be easily incremented.
Maybe we can add quantum.
How do you quantumize it?
Okay, sorry.
Any ideas?
He said, what if each of them they do it at interval, so eat the next thing you drop, then the next person.
These folks are so sensitive. If they're not hungry, they're not going to eat. You can't say, okay, you eat now, you eat now. Because I'm not hungry. Hey, okay. We can specify, guys, you have a time to eat, and then that's it. Whether you're hungry or not, skip it. Hey, at least that will prevent them from getting deadlock. Okay, so thank you for the attempt. Very good. Okay? Three people cannot eat who are next to one another. They can never eat at the same time. There's only one chopstick between each two. So the resources are already specified. We cannot add more chopsticks. Sometimes people say, okay, you have to remove one off the table. Yeah, that's foolish. What that means, that's the number we have, 5 people. Okay, I'll leave it to you guys. Google it and see if you find any nice solutions. I used to have it as part of a tutorial, but I don't think it's included in the tutorial. It'll be in one of the practices. By the way, I'm posting practice questions. And I'll post the solutions before the test. Is that sweet or what? What is it? Oh, you have me trapped, I just picked one of them and put it in my mouth. Okay, so here's the idea here. If this guy eats, so we've got the chopsticks from either side, so that means those two will not be able to eat. That one can eat, this one will not be able to eat. Okay, we're finished with deadlocks. All right, just quick questions. What's required for a deadlock to happen? How does a deadlock happen? How does a deadlock happen?
Four conditions have to be.
The four of them, that's just one. 4 conditions must happen in a system in order for a deadlock to happen. How do we prevent a deadlock from ever happening? Yeah, how do we prevent it? Do we use Banker's algorithm?
Get rid of the conditions.
How do we prevent a deadlock from happening? Remove one of the conditions from the system. if there are four, if you can get rid of one of them, we will never have a deadlock. That's called deadlock prevention. How do we avoid a deadlock? How do we avoid a deadlock? Anybody? Avoiding deadlock? What technique is used to avoid the deadlock? Banker's algorithm is the algorithm that's used to avoid the deadlock. So it might happen, but we avoid it. Somebody comes up and says, give me those resources. We say, hold on. If we give you those resources, our system is going to go into unstable, then we're not giving it to you. You have to wait. So that's called banker's algorithm. Right. How do we identify processes that are deadlocked? Detect them. This is called deadlock detection. So you know how deadlock happen, how prevention, avoidance, detection.
By tracing the allocated and recursive resources.
Yeah, using the diagram that uses the resource allocation requests and allocation. And we find out if there is, they can all be removed, the links or the process can all be served, or some of them cannot be served and there is a deadlock. And we can identify the deadlock. And what's a virtual device? Virtual device? You know what a virtual device is? Yeah. What's a virtual device? Yeah, keep going. Well, it's a device, by its nature is dedicated, but we use it as if it's shareable. We call that a virtual device. So a virtual device is not really shareable device. Originally, it's a dedicated device, but we can, trick the system into making it appear as if it's shareable. An example of that, how do we turn a device from a dedicated device into a virtual device? Using spooling technique. You should be able to describe spooling or explain spooling.
It's like queuing.
Spooling.
Yeah, it's like you queue something. There's individual devices that want to create something, for example, and they go and queue.
Imagine this, right? If you ask for to print assignments, right? When you go to somebody and they write it, and they'll actually physically write it. So you can go and sit with them, they start signing, it's taking 2 hours to finish it, and then they give it to you. And then you go and you're waiting in the queue. That's like that person is just dedicated. You're not trying to create this cheating, by the way. They cannot write your assignment at the same time. But they have a brother outside the house, you want your assignment done? I'll take it, consider it done. We'll even submit it in your behalf. Go, so you finish. And the other one comes in at the same time. Oh yeah, we can do for you. You don't have to wait for 2 hours to finish the first one. So he takes yours, then he tells you they'll consider them done, you're gone. This is what schooling is. So now they have them there, they're writing at their own time. You go to sleep or you do whatever you want, they submit it to you on your behalf. So that guy is still working in one at each time, but you guys don't have to wait for yours to be done, for the others to be done in two. You just submit it, they take them, and they deal with them later. But at least they stop that delay. It's not really queuing or something. They take your job and they queue it, but you don't have to queue anymore, you can go. Okay, is that clear?
Yeah.
Kind of. Any other questions, guys? Okay, I have a few. Okay, what's a quantum? It's a different thing now. This is a processor management. Very good. That's the maximum amount of time that the process can have the CPU. Is it better to have a long quantum or a shorter quantum? What? Okay. It's either good. Either very long quantum is good or a very short quantum is good. Now what's wrong with very long quantum? If it's very long, it's like first come, first serve. You're not going to interrupt anybody. It's like You know, what about what's wrong with very, very short quantum?
Very short quantum time problem is that every time you have to change PCB for the process, and because of that it leads to a lot of transitions and
What effect does that have on the CPU utilization?
yeah, it increases utilization. It's the percentage of how
Yeah, but
How
does
much-
it increase the use of your CPU or decrease?
it decreases.
So if the quantum is very short, then there's a lot of context switching. You change the processing. You give the CPU to one process, take it to another one. This context switching for that brief period of time, the CPU will not work. So if you do a lot of context switching, then the CPU will sit idle more for a longer time. So very short quantum is not good either. You do a lot of changing. Very long quantum you don't change. The CPU works until it finishes the process. So the CPU is rarely interrupted. So very long quantum gives you high utilization of CPU. Right, and what's the turnaround time? This is just to wake you up, guys, before you go to bed. See it? Yeah, want to start? Okay, so turnaround time is from the job request, the first request, until the job finished completely. Yeah.
With the checking in for attendance, do we only have to do the first one?
I think maybe for the benefit of those who are not here, we shouldn't really be considering that. We should be only considering the benefits of those who are here. But if I take the attendance now, so many other people are going to be considered not in, even those who walk through with you. So how about this? Just taking what we've done earlier on, you were all in earlier on, unless one of you just arrived. It's recorded, and then because it takes too long to record and all that, so we tell them this is the same students were here with the second step.
We should take it.
Pardon?
But we should take attendance.
We should take attendance?
No.
No, I know. That means. Okay, let's first turn the recording off.